Good morning, students. Today we are going to start fourth unit. In the fourth unit, we are going to study about iterative improvement technique. This is one of the algorithm designing technique which is available. We are going to study what is iterative improvement technique, what is the basic principle of iterative improvement technique, and how the problems can be solved using iterative improvement technique. This is what we are going to study in the fourth unit. Is my voice is audible, students? Before I start, let me check it out. Voice is audible, ma? Yes or no, students? Okay. If any disturbance is there, no, you just please unmute yourself and inform me so that I can correct it. Okay. And now, iterative improvement technique. The basic principle of iterative improvement technique is it will be starting with the feasible solution. Feasible solution in the sense a valid solution. Okay. So this technique will be solving the problem and it will identify a very basic valid solution for that particular problem. Then afterwards, what it will be doing now, it will be changing the current feasible solution to a feasible solution with a better value of the objective function by applying some very small improvement on it. This step will be repeated until we get the optimal solution to the given problem. This is what is the basic principle of iterative improvement technique. Initially, it is starting with a feasible solution. Then repeat the following step until no improvement can be found. Change the current feasible solution to a feasible solution with a better value of the objective function. And then return the last feasible solution as the optimal solution. This is what is the basic principle of iterative improvement technique. Under this one, we are going to see these examples. These are all the various examples available. Okay. The first one is simplex method, then a maximum flow problem, linear programming problem. The first example, what we are going to solve using iterative improvement technique is linear programming problem. This problem is going to be solved using simplex method. Then afterwards, maximum flow problem we will be solving using Ford-Fulkerson method and shortest augmenting path method also. We will be solving the maximum flow problem. This is the second example under fourth unit. Then the third example is maximum matching. Okay, matching available in a bipartite graph. This is what is the third example. Then the fourth example is stable marriage problem. And for this particular problem, Gale-Shapley algorithm we will be using. Okay. So these are all the examples included in our syllabus under iterative improvement technique. So we'll be solving these problems. Now we are going to see what is linear programming problem. Just take down the definition of linear programming problem. Linear programming problem is to optimize the linear function of several variables subject to our linear constraints. Okay. So this is what is the definition. Okay, so before seeing this one, seeing the definition, I'll show an example so that you will understand what is linear programming problem. Okay, so this is the example for a linear programming problem. Okay, so this is what is the example for linear programming problem. This is what is the example. Okay. So here, what we have to do now, we have to maximize the given linear function. Okay. So we have to maximize the linear function which is given to us. The linear function given to us is 3x plus 5y. This is what is the linear function which is given to us. And we have to maximize this one such that the given constraints are satisfied. What are the constraints given to us? X plus y less than or equal to 4 is the first constraint given to us. And then x plus 3y less than or equal to 6 is the next constraint which is given to us. Okay. So what we have to do now? We have to identify the value of x and y. We have to find the value of x and y such that the value of the given linear function 3x plus 5y is maximum. Just like that, you cannot substitute value for x and y. Why? Because when you give values for x and y, we have to check the constraint. Based on the given constraint only, we have to give the values for x and y. Okay, based on the given constraint only. Here, what is the constraint given here? The first constraint which is given here is what? X plus y. Whatever the value you are choosing for x and whatever the value you are choosing for y. Okay, so the sum of those two values must be less than or equal to 4. In such a way, only you have to assign value or you have to assume value for x and y. Not only this particular constraint, one more constraint is there. What is that? This is what is the second constraint. X plus 3y must be less than or equal to 6. These two constraints must be true. Apart from these two constraints, two non-negativity constraint is also given here. X and y values must be greater than or equal to 0. You cannot take any negative value for x and y. Understand? So these are all the constraints given to us. We have to find out the value of x and y that can be substituted here in this linear function such that the value of this particular function is maximum. Okay, so in that way, we have to identify the value of x and y. Now tell me, is it possible for, if at all you may think like that, if you give more large value for x and y, then we will be getting maximum value for this linear function 3x plus 5y. In that way, you can think. Okay, so assume that x is equal to 100. We are substituting x is equal to 100 and y is equal to 200. Assume like this. Now tell me whether it is possible to substitute x and y value like this. Is it possible to substitute x is equal to 100 and y is equal to 200? No. Very good. Why it is not possible? Very good, ma. Very good, students. Why it is not possible? What is the reason? Yeah. The constraint, very good, Vedanathan. The constraint x plus y must be less than or equal to 4. That is one of the constraint. What about the next constraint? X plus 3y must be less than or equal to 6. Okay, so the non-negativity constraint is satisfied here for this and x and y value 100 and 200. Non-negativity constraint in the sense x and y both are greater than or equal to 0. That constraint is satisfied, but all the constraints must be satisfied. So the first two constraints are not satisfied for the given x and y value. So we cannot substitute x is equal to 100 or y is equal to 200 in this way. It is not possible. Okay, so now tell me what is the value we can substitute to find maximum value for 3x plus 5y? What x value and what y value we can substitute according to the given constraint such that the value of 3x plus 5y is maximum? I'm expecting answer from you, students. What must be the x value and what must be the y value such that the value of the given linear function 3x plus 5y is maximum? Make it fast. Yeah, very good. Shruti, your answer is correct. 3 and 1. For x, we have to substitute 3 and for y, we have to substitute 1. If you substitute these two values, you'll be getting the maximum value. 3x means what? 3 into 3, 9. 9 plus 5 is equal to 14. 14 is the maximum value we will be getting. This is what is the optimal solution to this particular problem. Okay, so this problem is called as linear programming problem. Okay, so a linear programming problem means what? It is the general problem of optimizing the linear function of several variables subject to a set of linear constraints. Okay, so it is a general problem of optimizing. I'm using the term optimizing. Okay, I'm using the term optimizing in the sense sometimes you will be maximizing the given function, or otherwise you'll be minimizing the given function. Okay, both are going to be linear programming problem only. So what is linear programming problem? It is a problem of optimizing the given linear function like 3x plus 5 by, okay, of several variables subject to a set of linear constraint. Okay, this is what is a linear function with the two number of variables subject to these three set of linear constraints. So linear programming problem is a problem of maximizing the given linear function or otherwise minimizing the given linear function subject to the given set of linear constraints. Okay, in general, we can say that linear programming problem is a problem of optimizing the given linear function subject to the set of linear constraints. That's all. This is what is called as linear programming problem. Okay. So the problem which is shown here is the example problem part. So this is what is the example for a linear programming problem. Here the linear function given to us is 3x plus 5y. What are the constraints given to us? X plus y less than or equal to 4, x plus 3y less than or equal to 6, x greater than or equal to 0 and y greater than or equal to 0. These are all the constraints given to us. With the help of these constraints, we have to maximize the given linear function. Okay, we have to find the value of x and y such that the value of the given linear function 3x plus 5y is maximum. This is what is the solution for this linear programming problem. Okay, now we are what we are going to do now. Now we are going to see how to solve this particular problem. We are having two methods for solving this particular problem. The first method is called as geometric solution or geometric method, and the next method is called as simplex method. Before seeing the simplex method, I'll tell you what is this geometric method. Okay, so what we have to do now, we have to take the constraints. How many constraints are given here? Two constraints are given here. Am I right? So we have to take the constraints one by one. Okay, so assume that we are going to take the first constraint. Take the first constraint. This is what is the first constraint. We are taking the first constraint. You just equate this one with 4. Okay. So equate this one with 4. X plus y is equal to 4. In that way, you just equate it. Substitute x is equal to 0 and find the value of 4. Okay. So what I am telling you now, you just take the first equation. Okay. You just consider this one as linear equation. X plus y is equal to 4. Okay, this is what. And now in this one, no, you just substitute x is equal to 0. Let x is equal to 0. What is the y value you'll be getting? You'll be getting y is equal to 4. Okay. Now this is one point we have got. What is that point? This is the point. Actually, we are going to draw a line for the given constraint, the first constraint. Okay. So what is the point we got? We have got 0, 4. 0, 4 is the first point we got. Now using the same constraint, you just substitute y is equal to 0. Let y is equal to 0. What is the x value will be getting? X will be equal to 4. Okay, this is what is the next point we got after substituting y is equal to 0 in the first constraint. So what is the next point we got? We got the point 4, 0. This is what is the next point we got. Okay, now after this one, no, we have to draw a line for this between these 2 points. No, we have to draw a line. So it will be like 4, 0 means assume that 4, 0 is this is what is 4, 0. 0, 4. 0, 4. This one. So in this way, you will be getting 2 points. You have to draw a line through those 2 points. This is for the first constraint. And now I'm going to erase all these things. Okay. Now we have drawn. We have identified the line for the first constraint. In the same manner, we have to draw the line for the second constraint. What is the second constraint given here? X plus 3y is less than or equal to 6. In the same manner, just substitute x is equal to 0. If you substitute x is equal to 0, what is the y value you'll be getting? You'll be getting y is equal to 2. This is one point. 0, comma 2 is the point. This is what is the 0, comma 2 point. Then afterwards, substitute y is equal to 0. Y is equal to 0. What is the x value you'll be getting? X will be equal to what? X will be equal to 6. This is what is the second point we got. One is 0, comma 2. Another one is 6, comma 0. 6, comma 0 in this sense, it will be like this. Here, this may be 6, comma 0. In this way, we got this particular point. Now, afterwards, we have to draw a line through that particular point also. Okay, so in that way we have drawn a line here. Okay, so now if you, after drawing straight lines for both the given constraints, what we have to do now, we have to identify the area which is bounded below by both the lines. Okay, so for both the lines, what is the area which is bounded? This is what is the area which is bounded by both the lines. We have drawn two lines based on the constraints, no? So after drawing the two lines, we are identifying the area which is bounded by both the lines. Not for area bounded by single line is not needed for us. Now, if you consider this area, no, this area is bounded only by the first line. Okay, not by the second line. That kind of area is not needed for us. We have to identify the area which is bounded by both the lines. Okay, both the lines what we have drawn for the given constraints. So this is what is the area which is bounded by both the lines. Okay, now this is what is the solution for this particular problem. All these, whatever the points available inside this region, no, this region is called a feasible region. All the points available inside this feasible region is going to give valid solution to this particular problem. Okay, so that is you will be getting x and y value such that these two constraints are satisfied. Such kind of valid x and y value you will be getting, okay, in this area. But what is our aim? We have to maximize this value. Am I right or not? So we have to identify the point which is maximizing the given linear function. This is what is needed. Generally, the extreme points of this feasible region will give the maximum value of the given function. Okay. What are the extreme points? 0, 1 is the first extreme point. 4, 0 is another extreme point. 3, 1 is the third extreme point. 0, 2 is the fourth extreme point. So these four are the extreme points that are available here. So the maximum solution or maximum value will be available in any one of these extreme points only. Okay, so if you substitute now what you have to do now, you have to substitute all this x and y value in this equation 3x plus 5y. Which value is going to give, which point is going to give maximum value? That is what we have to identify. 0, 0, obviously you will not get maximum value. 0, 2, you can substitute and check what is the value you'll be getting. 4, 0 also you can substitute and check what is the value you'll be getting. And then 3, 1, you have to substitute and check it out. What is the value you'll be getting? 3 into, in place of x, we have to substitute 3. So 3 into x, you'll be getting 9. 9 plus 5 into 1. Y value is what? It is 1. 5 into 1 is equal to 5. So what is the total value, maximum value you'll be getting? 14 is the maximum value which will be possible here. For getting this maximum value 14, what is the point we have to substitute? 3, 1 is the point we have to substitute. X and y point we have to substitute. Okay, so this is what is the solution for this linear programming problem. And now we have solved this problem using geometric method. Okay, now the same problem can be solved. Now we are going to see the next method. The next method is very important method, that is simplex method. That is very, very important method. That is what is the method we are going to see now. Okay, so problem is going to be the same. Okay, the same linear function is going to be given to us. The same constraints are going to be given to us. What is our aim now? We have to find the point which is maximizing the given function such that the given constraints are satisfied. Okay, so that is what is the problem. Now we are going to solve that problem using simplex method. Okay. Now we are going to see simplex method. Okay. Here the definition of linear programming problem is given here. I'll tell you what is the basic idea behind the simplex method. Okay. So simplex method, it will be starting by identifying an extreme point of the feasible region. Just now we saw the feasible region, the region, okay, which is satisfying the constraints of the given problem is going to be the feasible region. The region which is going to give valid solution to the given problem is called as feasible region of the given linear programming problem. Okay. So initially the simplex method is going to start by identifying an extreme points of the feasible region. Just now we saw the extreme points. Okay. So we have seen already that the maximum value is possible in any one of the extreme point of the feasible region. That also we have seen already. Okay. So here your simplex method is going to start by identifying an extreme point of the feasible region. And then it will be checking whether the value of the objective function can be improved by going to an adjacent extreme point or not. Okay, in that way it will be checking. If it is not the case, then the current point is going to be the optimal. Your simplex method will be returning the current point as the optimal solution. Or otherwise, if it is the case, if suppose if you can improve the solution, if that is the case, then your simplex method will be proceeding to the adjacent extreme point with an improved value of the objective function. Okay. So in this way, the steps will be repeated in the case of simplex method. After a finite number of steps, the algorithm will be finding either it will be reaching an extreme point with an optimal solution, or otherwise it will determine that no optimal solution exists for the given problem. This is what is the basic principle of simplex method. Okay. Mm. I'll repeat this basic principle of basic idea behind simplex method once again. So your simplex method is starting by identifying an extreme point of the feasible region. Then it is checking whether the value of the objective function can be improved by going to an adjacent extreme point. And if it is not the case, then the current point is the optimal solution. It will be returning as the current point as the optimal solution. Or otherwise, if this is the case, or otherwise, if suppose the current solution can be improved, if that is the case, then it will proceed to the adjacent extreme point with an improved value of the objective function. So after finite number of steps or iteration, it will come to the conclusion that this particular solution is the optimal solution. Or otherwise, if suppose if there is no optimal solution exists for that particular problem, then it will say that there is no optimal solution for the given problem. Okay. So for example, assume that this is what is the basic principle of simplex method. Okay. So assume that as we have seen already, this is what is the that is feasible region. Assume like this. Okay, your simplex method will be start. These are all the extreme points available here. This is point number 1, point number 2, point number 3, point number 4, and point number 5. These are all the extreme points available. Okay, so first of all, it will be starting with the initial extreme point. It will be identifying an extreme point of the feasible solution as the first step or very first solution. Then afterwards, what it will be doing after finding this feasible solution, it will check whether the value of the objective function, which is the objective function, if suppose this is what is the problem given to us, maximize 3x plus 5y subject to x plus y less than or equal to 4x plus 3y less than or equal to 6. Assume like this. Then which is the objective function? 3x plus 5y is the objective function. The given linear function 3x plus 5y is the objective function. Okay. So now what your simplex method is doing after identifying this solution as the initial solution, it is checking whether the value of the objective function, whether the value of the given linear function can be improved further or not by moving to the next adjacent extreme point. In that way, it is checking. If that is the case, then it will be moving to the next extreme point and it will be finding the value of this objective function. And in that way, the next time after identifying the second feasible solution also, it will be trying to move to the next adjacent extreme point in order to improve the value of the given linear function 3x plus 5y. In order to improve the value of the given objective function 3x plus 5y. In that way, it will be checking whether the value of the given objective function can be improved or not by moving towards the next adjacent extreme point. If this is the case, if the value of the objective function can be improved, then it will be moving. Your simplex method will be moving to the next extreme point, and it will be finding the value of the solution. Okay, value of the objective function. If suppose assume that from this one already it found three solution for the given problem. After this particular solution, this is what is the last solution. Assume like this. After this particular solution, there is no way of improving this particular solution. Even if the simplex method is moving to the next point also, the value of the current objective function cannot be changed. It cannot be improved. If that is the case, then your simplex method will be returning this one as the solution. The current solution, that is whatever the current solution we got, that solution as the optimal solution to the given problem. In that way, it will be executing, it will be barking. This is what is the basic principle of simplex method. Okay. Now we are going to see the example. Now, as we have seen already, this is what is the example problem given to us. We have to maximize the value of the linear function 3x plus 5y. Actually, we know what is the solution of this particular problem. Am I right or not? Just now we have solved this problem using a geometric method, and we found the value of x is equal to 3 and value of y is equal to 1. This is what is the point which is going to maximize the given objective function or linear function 3x plus 5y. That we found already. But now we are going to solve the same problem using different method. What method? Simplex method. Using simplex method, we are going to solve, okay, the same problem. So if you use different method also, we'll be getting the same solution only. Okay, ma. So now this is what is the given problem. The objective function is what? 3x plus 5y. Okay. What are the constraints given to us? X plus y less than or equal to 4. X plus 3y less than or equal to 6. Other than these two constraints, two more non-negativity constraints are also given. That is x and y must be greater than or equal to 0. In that way, it is given. So first of all, your simplex method will be identifying the initial feasible solution. Am I right? Then after identifying the initial feasible solution, what it will be doing now? It will be representing that solution as a tabular column. I'll tell you what is the format of the tabular column afterwards. Okay. So it will be representing that solution as a tabular column. Now I'm telling you the summary of the simplex method. Okay, so summary of the simplex method. So it will be representing that one as a tabular column. Actually, if suppose we know what is linear programming problem. This is what is the example for a linear programming problem. Okay, and now if the linear programming problem is in the standard form only, we can use simplex method. If the given linear programming problem is not in the standard form, then we cannot use simplex method at all for solving it. Okay. Now I'll tell you when the problem can be called as a linear programming problem in standard form. The first condition is the given problem must be a maximization problem. This is the first condition for the linear, that is standard form of the linear programming problem. The second condition is going to be the constraints, the given constraint, all the given constraints must be linear constraints, must be of linear constraints. So the constraints are given here, all these constraints must be linear constraints. Okay, this is what is the second constraint, second condition for the standard form. If the given constraints are containing inequality like this, x plus y less than or equal to 4, in this way, if at all if it is containing inequality in it, then we can convert this one into a linear constraint by adding some slack variable. Okay, so with the help of the slack variable, we can convert the inequality present in an equation constraint and that can be converted as a linear constraint like this with the help of the slack variable. We are adding a slack variable u here. So that instead of after adding this u, you can replace the less than or equal to sign with equal to sign. So the same constraint can be written like this: x plus y plus u equal to 4. Similarly, we have one more constraint here. The second constraint is also not in the form of linear equation because we are having an inequality here less than or equal to. So for that also what we have to do now, we have to add another slack variable for this particular constraint. We cannot use the same slack variable. We have to use different slack variable for making the second constraint also as a linear constraint. So the name of the second slack variable is what? It is equal to v. Okay. So x plus 3y plus v is equal to 6. In that way, we have modified, we have converted the given constraints containing inequality into linear constraints. Okay, so this is the second condition for the standard form. The constraints must be of the linear form. The constraints must be of linear constraint type. This is the second constraint. Then condition for the standard form. Then the third constraint is the variables whatever we are using here all must be non-negative in nature. That means what? X must be greater than or equal to 0, y must be greater than or equal to 0. If suppose z is there in your objective function, then z must also be greater than or equal to 0. So this is what is the third condition for the standard form. If all these three conditions are satisfied, then only the given problem can be called as in the linear programming problem in standard form. If the given linear programming problem is in standard form only, we can use simplex method. Otherwise, the simplex method is not possible. Okay. And now summary of the simplex method. The first point is you just note down in your notebook mark initialization. This is what is the first step of your simplex method. Initialization, it will be checking whether the given linear programming problem is in the standard form or not. If at all, if it is not in the standard form, it will be converting that into standard form. This is what is the first step of your simplex method. Then the second step is optimality test. Name of the second step is called as optimality test. In the case of optimality test, what your simplex method will be doing now, it will be representing the current solution as a table. Okay, in the tabular form, the current solution will be represented. And the very last row which is available in the table is called as objective row. It will check whether the objective row, all the values are non-negative in nature. In that way, it will be checking. All the values in the very last row are non-negative in nature, then the current solution is the optimal solution. That is what is the meaning. If that is the case, the algorithm will be stopping its operation there itself and it will return the current solution as the optimal solution of the given problem. Otherwise, if suppose in the last row, one or more values are containing negative value in it, in that case, the given the current solution is not the optimal solution. It's just a valid solution, that's it. But it is not the best solution. Okay, that is what is the meaning. Our aim is to identify the best solution for the given problem only. In that case, then your simplex method will be trying to find the next feasible solution which is possible for the given problem by moving towards the next extreme point of the feasible region. Okay. For doing that, in the next step, it will be identifying the entering variable. Then fourth step is identifying the departing variable. Then afterwards, in the fifth step, it will be forming the next table for the next solution. All these steps will be repeated until we find the optimal solution to the given problem. Okay. So now what are the steps, ma? The first step is initialization. Initialization in the sense what? Here during this step, the algorithm, the simplex method will be checking whether the given problem is in the standard form or not. If it is not in the standard form, it will be converting the given problem in the standard form. Standard form, now what are the three requirements of the standard form? The given linear LPP. In short, we can say that one as LPP, linear programming problem. The given linear programming problem must be a maximization problem, the first condition. Second condition is all the constraints except the non-negativity constraint, all other constraints must be of linear constraint type, linear equation. This is what is the second condition for the linear programming problem, standard form. Okay, if suppose if it is not in the linear equation form, then we have to use slack variable for converting the inequalities present in the given constraints into equality. Okay. Then afterwards, so the third condition is all the variables must be non-negative in nature. Okay. So these three are the requirements for the standard form. So it is checking whether the given problem is in the standard form or not. This is the first step. Then the second step, no, optimality test. How to do the optimality test? What is the use of optimality test? To check whether the current solution is optimal or not. How to do this one? We have to, I told whatever the solution a simplex method is finding, no, that will be represented as a table. Okay. So for example, the table will be like this. If I put it in the presentation mode, no, it is not displaying the table content. So let me. Okay, I'll show the table afterwards now. So if suppose in the last row here, whatever this row, the last row which is available here, no, this is what is going to be the objective row for the given objective row. Okay. So if all the elements are positive, then the current solution is going to be the optimal solution. Otherwise, if suppose any one of the element is negative also, this is not the optimal solution. In that case, in the next step, we have to find the entering variable, then we have to find the departing variable, then we have to form the table for the next solution, and so on. In that way, it must be repeated. In this way, only your simplex method is going to work. We are going to use simplex method for solving the problem. Okay. Now we'll solve the problem part. Actually, now we have converted. What is the problem given to us? This is what is the problem given to us. Maximize 3x plus 5y, x plus y less than or equal to 4, x plus 3y less than or equal to 6, x greater than or equal to 0, y greater than or equal to 0. This is what is the problem given to us. Now, what we are going to do now, we are converting the given problem into standard form. Okay. So the first condition is satisfied. It is a maximization problem. First condition is satisfied. But here the second constraint, the constraints are not in the linear form. So with the help of the slack variables u and v, we are converting the inequalities present in the constraints into equalities like this. We are converting into linear functions. Then all the third constraint is satisfied already. What is that? Both the variables x and y are greater than or equal to 0. And here we have introduced u and v, and those u and v also greater than or equal to 0. Okay. And now we are going to represent this one as a table. Okay. As I told already, we are going to represent this one as a table. Okay. This is what is the given problem. Okay. So this is what is the given problem. This is what is the function. We have introduced u and v in the constraints now that can be added here. Okay, in the objective function also with coefficient 0 only. Okay, so we cannot add any extra term in the objective function. So with coefficient 0 only, we have to add that. Okay, so now this is what is the objective function we are going to maximize. For that, we are going to find what is the x and y value. And then what is the next one? The constraint, we have written the constraint as x plus y plus u equal to 4. This is what is the first constraint. Second constraint is this one. Now I'll tell you how to write the initial solution as a table. Okay. So initially we are assuming that x and y value both are equal to 0. This is what is the initial solution we are identifying. Okay, and now that initial solution is going to be represented as a table here. Now, what are the variables we have? X. Let me change the ink. So the first variable, the first column is what are the variables available here? X, Y, U, and V. Four variables are available. First column is X, second column is Y, third column is U, fourth column is V, and then after this one, this line you have to draw. For the right hand side of the equation, we have to use this one. And now this one is for the first constraint. So what is the first constraint? X plus y plus u is equal to 4. What is the coefficient of x there? 1. So I am writing 1 here. Coefficient of y is also 1. Coefficient of u is 1. There is no v term in the first equation. So we are putting 0 there. And what is there in the right hand side? 4 is available in the right hand side. So we are writing 4 here. Then afterwards, we have one more variable here, one more constraint here. What is that? X plus 3y plus v is equal to 6. That can be written as the second line here in the table. The coefficient of x is equal to 1. Coefficient of y is equal to 3. There is no u term, so we are writing 0 here. Coefficient of v is equal to 1. Right hand side we have 6. So in that way we have written. Now the last row is going to be the what is it? Objective row. For writing the objective row, we have to write the objective row from the given objective function only. When you write the objective function row, we have to negate the coefficient of the objective function, and then only we have to write. You have to listen very carefully for whatever the point I'm telling you, you have to note down. You should not forget it. Okay. So we have to negate the coefficient of the objective function. Coefficients available in the objective function. Here we have plus 3x. That must be written as, the coefficient of x must be written as minus 3. Here plus 5y. That can be, the coefficient of y can be written as minus 5y. Minus 5. Here it is going to be minus 5. So minus 5 we have to write. Then what is the coefficient of u? U is equal to 0. I am writing. V is equal to 0. I am writing. Now substitute here. Name of this one is going to be u. Substitute u, and here this row is going to be v. Okay. If you substitute x and y both equal to 0, what is the value you will be getting here? If you're substituting x is equal to 0 and y is equal to 0, what is the value of the objective function? 0 into 3 plus 5 into 0 plus any value into u, and 0 into any value of u plus 0 into any value of v. The value is going to be 0. This is what is the value of the objective function for the solution 0, 0, 4, 6. This 0 is for this is the x value, this one is the y value, this is the u value, this one is v value. Okay, if you substitute x, y, u and v in this objective function, you will be getting the value as 0. So that value only we have written here. This is what is the tabular representation of the initial feasible solution of the given problem using simplex method. One step is over. Now your simplex method is going to do the optimality test. How to do the optimality test? Whether the objective row, which is the objective row? The last row is going to be the objective row. Okay, minus 3, minus 5, 0, 0, 0. This is what is the objective row. Now check it out whether all the values here are positive. No, 2 negative values are there. That means what? The given solution, the solution which is available now here, or whatever the current solution we found here, is not the optimal solution of the given problem. It is going to be the feasible solution. That's it. In that case, what your simplex method will be doing now, it will be identifying the column with the most negative value as the pivot column. Okay. So which is the most negative value? Minus 5 is the most negative value. So it will be identifying this column as the pivot column. Okay. Then afterwards, what it will be doing now? It will be trying to identify the pivot row. Okay. What is the name of this particular column? Excuse me. Name of this column is pivot column. Pivot column. Now we are going to find the pivot row. For that, what we have to do now? We have to divide the last column values by the values of the with the values that are available in the corresponding pivot column in the same row. For example, here the last column value is 4. What is the pivot column value available in this row? It is 1. So 4 divided by 1, what is the value you'll be getting? 4 you'll be getting. Okay. So 4 is the value you'll be getting here. Or otherwise I'll change my ink color. Okay. So 4 by 1 is 4 you'll be getting. So this value, whatever the value we are finding here, is going to be called as theta ratio. Okay, pa? This is what is a theta ratio we are finding. Now the 6 must be divided by what? This must be divided by 3. Why? Because 3 is the pivot column value available in this particular row, in the second row. So 6 divided by 3, what is the value you'll be getting? 2 is the value you'll be getting. Okay. And if suppose if the pivot column value is the positive value only, you can find the theta ratio for that particular row. Otherwise, you need not find theta ratio at all. So here theta ratio we need not find. Why now? The pivot column value is negative. Okay, so you need not find theta ratio for this particular row. So in that way, after finding theta ratio, we have to identify the row with minimum positive theta ratio. Which is the minimum positive value here? 2 is the minimum value here. So we have to identify this row as the pivot row. Now we have identified which is the pivot row. Okay, we found what is the pivot row. So initially we found what is pivot column. How to find the pivot column? The pivot column is going to be the column with the most negative value in the very last row. That column is the pivot column. Then afterwards, we are finding theta ratio. How to find the theta ratio? The last column value must be divided by the values available in the pivot column of the same row. In that way, we are finding theta ratio. After finding theta ratio, okay, we have to identify the row with minimum theta ratio, minimum positive theta ratio. Here 4 is one theta ratio available, 2 is another theta ratio which is available, which is minimum, 2 is minimum. So we are identifying this row as the pivot row. Now, what element is available in the pivot row and pivot column? This 3 is the element which is available in the pivot row and pivot column. So this element is called as pivot element. This element 3 is called as pivot element. Okay, this 3 is called as pivot element. Now we are ready for forming the table for the next solution, because this solution is not the optimal solution. Why means in the optimality test we found that because we are getting negative values in the last row now. So in the optimality test we found that this is not the optimal solution. We have to find the next solution. Okay, in that way we found. Okay, so now we are going to find the table for the next solution. Okay, now okay. Let me write all the values here. This is what is the first table. Whatever the values we got already, I'm going to write all those values as it is here. X, Y, U, V. Here this is going to be U, this is going to be V. Here it is 1, 1, 1, 0, and then 4, and then 1, 3, 0, 1, 0, minus 3, minus 5, 0, 0, 0. In this, we found that this is what is the pivot row, and this is what is the pivot column, and this 3 is the pivot element. Now we have to form the next table. This is what is the next table we are going to form. Okay. So for forming the next table, no, the very first row, this pivot row we are getting here, no, that must be written as the new row here in the next table by dividing all the elements available in the pivot row by the pivot element. Okay. Which is the pivot element here? We know which is the pivot row. This is what is the pivot row. Okay. Divide all the elements by 3. Why by 3? 3 is the pivot element. So we are going to divide all the elements by 3 here. Okay. So if you divide all the elements by 3, what is the value you'll be getting here? This is going to be 1 by 3. Okay. Already existing value is 1. So 1 here also. And here, no, you have to write this one as x. This first column is x, y, u, v, and then here instead of v, here this is pivot row value, no, this is going to be the departing variable. This y is going to be the entering variable. That is variable corresponding to the pivot column is going to be the entering variable. So this y, this v will be replaced by this y. So here you have to write y. Okay, and here you need not change. U must be written as it is. So these are all the initial setup you have to do. Now this 1 is written as 1 by 3. This 3 is going to be written as 3 by 3 is 1. 0. 0 is going to be written as 0 by 3. 0 by 3 is 0. Then this 1 is going to be written as 1 by 3. 1 by 3 is 1 by 3. And 0. 0 by 3 is 0. Sorry, this is not 0 actually, it is 6. Okay. So 6 by 3. 6 by 3 is equal to 2. This is what is the new row we found. With the help of this new row, no, we have to find the first row and the third row also. I'll tell you what is the formula we can use for finding the first row and the third row. The formula for finding the first row is, the formula is common. Already, let me change the existing row value minus C into new row value. C into new row value. Okay. This is what is the formula we have to use for finding the other rows. Now, apply the formula here. What is the value already? We are going to find this particular value. This value we are going to find. What is the value already available here? What is the value already available? 1 is the value already available. So, 1 you write. Okay. 1 minus 1. 1 minus, this is what is the already available. 1 minus C into, C means the value which is available in the pivot column. Okay. So the value which is available in the pivot column, that you have to write. C. That is equal to 3. And pivot column of the first row. Okay, pivot column of the first row. So what is that? It is equal to 1. Okay, 1 into new row. What is the new row value which is available here? 1 by 3 is the new row value which is available. Okay, already existing value in the row, what we are going to find, into the corresponding pivot column value which is available in the same row, that is equal to 1 into the new row value which is available for that particular position, for that particular column. Okay, it is 1 by 3. So if you simplify this one, what you'll be getting, 3 minus 1 divided by 3, which is equal to 2 by 3. So I'm going to write 2 by 3 here. I have to change the ink color here. So 2 by 3 I have to write. Okay. Now, similarly, what is the value you will be getting here? What is the already existing value? It is 1. So, 1 minus, okay, 1 minus, what is the pivot column value which is available here in the first row? That is 1 only. So, 1 into, what is the new row value which is available for that particular column? It is 1. So 1 minus 1 into 1, which is equal to 0. So here I am writing this one as 0. Okay. Now similarly, if you repeat the step for this particular value, what is the value you'll be getting? U is equal to, if you repeat this one, no, you'll be getting 1 here, and here you'll be getting minus 1 by 3. Okay. So minus 1 by 3 you'll be getting here, and here this will be equal to 2. Okay, this is minus 1 by 3. And similarly, so now we found all the values in the first row. Similarly, we have to find all the values in the last row also. The formula is same only. What is the already existing value for this particular this one? This one only we are going to find. Already existing value here is what? Minus 3. Okay. So minus 3 minus, okay, minus 3 minus C. What is the C value which is available here? That is in the third row. We are going to find the third row only. And in the third row, what is the pivot column value? Minus 5 is the pivot column value. Okay. So apply the formula minus into minus 5. That can be written as plus 5. Plus 5 into, what is the new row value which is available in this particular first column? We are going to find first column value of the third row only. So this is what is the new row we found already. Okay, this is what is the new row we found already. In the new row, first column value is what? It is 1 by 3. Okay, so 5 into 1 by 3. I am applying the same formula here. Row into C into row, new row value. That is what I am applying. Okay. So minus 5, minus into minus plus, plus 5 into 1 by 3. Okay. Now simplify this one. Simplify this and tell me what is the value you're getting. Minus 3 plus 5 by 3. You'll be getting minus 9 plus 5 divided by 3, which is equal to minus 4 by 3. This is what is the value you'll be getting. So here we have to write minus 4 by 3. This value is going to be minus 4 by 3. Okay, so this is going to be minus 4 by 3. Similarly, you can find this value. That this will be equal to 0. This will be equal to 0, and the next value is going to be 5 by 3, and this value is going to be 10. Okay. So now if you substitute, the meaning of this particular table is, if you substitute y is equal to 2 in this equation, you will be getting the objective function, value of the objective function as 0. Now this is the table form of the second solution. Okay. So in the second solution, what is the value you're getting? 10 is the value you're getting. Now we have to check whether this is going to be the optimal solution or not. That we have to check it out. Now, if all the values available in the last row, or this is what is the objective row. The last row is going to be the objective row. If all the values in the last row are positive, then only the solution is going to be the optimal solution. Otherwise, the solution is going to be it is not going to be the optimal solution. So in that way, in that case, we have to repeat the same procedure once again. Okay. Now we have to consider this one as the second table, and you have to identify the pivot column. This is most negative value which is available in the last column is what? Minus 4. So this must be identified as the pivot column. Then we have to find the pivot row value. How to find the pivot row value? this is what is the last column. No, in the last column, all the last column values must be divided by the corresponding pivot column value available in the same row. 2 divided by 2 by 3. 2 divided by 1 by 3. 10 divided by minus 4 by 3. Minus any negative values there, you need not divide that one. Okay. So in that way, you can identify the theta ratio. After finding the theta ratio, you have to identify the row with the minimum theta ratio. This will be that particular row. Okay, with the minimum theta ratio, you have to identify. From that, you will be identifying which is the pivot element. With the help of the pivot element, you will be finding the new row of the next table, and with the help of this particular new row and with the help of this particular formula, we can use the same formula. Okay, you can find the second row in this table, third row in this particular table. Okay, so if you do the calculation like this, Noma, in the third, let me delete everything from here, and then I'll tell you what is the value we will be getting in the next table, the third table. If you repeat the same procedure, you'll be getting these values in the third table. This is going to be X, Y, U and V. Okay, so here X and this one is Y. Here 1 you'll be getting 0. This is going to be 3 by 2. This is going to be minus 1 by 2. Here 3 you'll be getting. This is going to be 0. This one is 1. This one is minus 1 by 2. This is 1 by 2. This one is 1. Here you'll be getting 0, 0, 2, 1 and then 14. This is what is the table we will be getting. So this is the third solution your simplex method is identifying. Okay, after getting every solution, your simplex method will be checking whether the current solution is the optimal solution or not. How to do the optimality test? Check the last row, objective row, whether all the values are positive or not. Yes, all the values are positive. 0, 0, 2 and 1. Okay, and 14 all are positive in the sense what the current solution, the solution which is represented by the current table is the optimal solution. It is satisfying the optimality test. Okay, so this is what is going to be the optimal solution because there is no negative value in the last row. So this is the end for this particular problem. Okay, simplex method, and this table represents the optimal solution, the maximized solution for the given problem. Okay, now this table, it represents what is the value of x. X is equal to 3. See the first column and the last column. What is the last column value for y? Y is equal to 1. And see the last row value, last column, last row value, it is 14. So what is the value of x? Value of x is equal to 3. Value of y is equal to 1, and then the maximum value what you can find with the help of this 3, 1 is going to be equal to 14. This is what is the solution for this particular problem. In this way only your simplex method is working. Okay, ma? Dear students, do one thing. You just take down the same problem. Okay, so you solve the same problem. 3 tables you have to form. The initial table, then with the help of the initial table, okay, so you have to identify the pivot column, pivot row, pivot element, and then with the help of all these informations, you have to form the second table. After forming the second table, okay, you have to check whether all the values available in the last row, objective row, are negative or positive. If all are positive, we can stop the operation there itself. But we didn't get all positive values there. We had a negative value in the second table. So what we have to do now? Optimality test is failed. So again we have to form the next table for the next solution. Again you have to find the pivot column in the second table, pivot row in the second table, and then pivot element we have to find. With the help of all these informations, we have to form the third table. This is what is the third table. This is corresponding to the third solution what we found for this linear programming problem. Okay, and if you check this particular table now, all the values are positive values. In the last row all are positive values. In the sense, what does it mean? The problem, it is actually the solution what we found here now at present, the current solution is an optimal solution. That is what is the meaning. So we need not repeat the same step again. We can stop the operation here itself, and we can give the solution as x is equal to 3 and y is equal to 1. How we are giving the last column value for x is equal to 3. So x is equal to 3, and the second column, last column value of the second row. Okay, y. For y, the value is equal to 1. So we are writing y is equal to 1. And what is the last row, last column value? It is 14. That means what? If you substitute x is equal to 3 and y is equal to 1 in this objective function, you will be getting the value as 14. That's it. This is what is the solution for this problem. Now the same problem, okay, we have solved in two methods. One is geometric method, another one is using simplex method. Now do this one as a homework. Solve the problem by yourself. Afterwards, no, after solving this one, I'll give you one more problem, different problem I will give, and you have to solve that one as an assignment. Okay, so now at present, no, today itself you solve, try to solve this problem. Identify all the three tables, check it out whether you are able to find all the three tables correctly or not, whether you are making mistakes in between or not. In that way, you check it out. Try, you know what is the solution for this problem. Try to find out the solution for this problem. Okay, and submit it to me. The last class, no, most of you have submitted. The other students, you have not submitted. It is your duty to study, my students. Otherwise, practice the problems. Otherwise, it will be very difficult for you to remember everything. If you practice and if you understand and practice and solve the problem only, you'll be feeling easy. Okay, so solve this problem and submit as an assignment to me, and I'll give one more problem afterwards. Okay, if you have any doubt, you can ask me. Any doubts, students? No one is responding. Is my voice is audible, first of all? Okay. Do you understand the linear programming problem using graphical method and simplex method? Is it clear, or you want me to repeat it again? Shall I move to the next topic or not? What about others, ma? Students, only one student is responding me. Others and all not responding anything. No reply at all. If you practice only, you will get it. You keep that in your mind. Okay. And now I'm moving to the next problem. The next problem is maximum flow problem. Okay. So this is what is the maximum. The next problem which is available here is maximum flow problem. Actually, it is a problem of maximizing the flow of material through a transportation network. This is what is called as maximum flow problem. It is a problem of maximizing the flow of material through a transportation network. For example, through a pipeline system or a communication system or transportation networks, we have to maximize the flow of the material through the transportation network. This problem is called as maximum flow problem. Okay, and now this is the example for flow network. Okay, so here in this graph, no, actually it is a directed graph, and this graph will be containing one source vertex and one sink vertex. Okay, source vertex means a vertex without any incoming edges is called as a source vertex. Okay, so why it is the first vertex number 1 is going to be the source vertex. Why it is source vertex? There is no incoming edge, no edges entering this particular vertex. So this is called as source vertex. And Similarly, we must have exactly one vertex without any outgoing edges from it. Okay. So what about this one? Vertex number 6. Two incoming edges are coming towards 6, but no edges going out from 6. So this vertex is going to be the sync vertex. Okay. So this kind of network is called as flow network. Now we are going to find the maximum flow which is possible in this particular flow network. We are going to solve maximum flow problem for this particular network. Okay. And one more thing here, weights are given for every edge. This weights, it represents the maximum capacity of the edge. Okay. So maximum capacity of the edge is what? 5. For this particular edge, no, the maximum capacity is 5. In the sense, maximum 5 number of materials can be sent through this particular edge. What is the maximum capacity of this particular edge? Maximum, only one material can be sent through this particular edge. Here it is 4, in the sense what? Maximum only 4 materials can be sent through this particular edge. This is what is the maximum capacity of that particular edge. And see the direction also. 5 number of materials can be sent from the vertex number 2 to 3. And from 1 number of material can be sent from 4 to 3. So in that way only the direction is also given. Okay. So here we have to find the solution such that, okay, 2 constraints are satisfied. Okay. The first constraint is called as flow conservation requirement. Okay. Okay. And the another one is flow conservation requirement. Capacity constraint. Both the constraints must be satisfied. These two other constraints must be satisfied. Okay. When you find the solution, no, the solution which is satisfying flow conservation requirement and the flow conservation requirements and the capacity constraint. Both the constraints must be satisfied. In that way only we have to find solution for this particular problem. Flow conservation requirements in the sense, okay, see here, this is what is the graph which is given to us. The number of materials that are entering a particular vertex must be equal to the number of materials that are leaving from this particular vertex. For example, if 5 number of materials are entering to this particular vertex, or otherwise not 5, maximum 2 only we can send through this particular edge. So if suppose 2 number of materials are entering this particular vertex 2, then the total number of materials that are leaving from that vertex must also be equal to 2. So 1 plus 1 is equal to 2. Or otherwise you can have 2 and then 0. 0 plus 2 is equal to 2. So the number of materials that are entering a vertex must be equal to the number of materials that are leaving from an intermediate vertex. If suppose if this is satisfied, then the total number of materials that are entering the source will be equal to, must be equal to the total number of materials that are leaving from the sink vertex also. Okay. So in that way, the flow conservation requirements must be satisfied. Okay. When we find a solution. And similarly, capacity constraint. The next constraint is called as capacity constraint. Capacity constraint in the sense the actual flow must be less than or equal to maximum capacity of that particular edge of any edge. Okay. So if suppose if through this edge, what is the maximum capacity of this edge? 3 is the maximum capacity of this particular edge. So at the maximum only 3 number of materials you can send through this edge. If you want 1 material you can send, or otherwise you can send 2 number of materials, or otherwise you can send 3 number of materials. Okay. So only that is the flow must be less than or equal to the maximum capacity of the edges. This is what is called as capacity constraint. The actual flow can be represented using the variable x, and the maximum capacity of the edges can be represented with the variable u. Always your Xij must be less than or equal to Uij. What is Xij? Actually, the number of materials that are flowing through a particular edge. That is what is the Xij. What is Uij? The maximum capacity of that edge is going to be the Uij. Okay. Always Xij must be less than or equal to Uij. This constraint is called as capacity constraint. Okay, so we found the solution. We have to find a solution such that the flow conservation requirement is satisfied as well as the capacity constraint is satisfied. Okay, so with respect to these two constraints only, we have to find what is the maximum flow which is possible through this network. Okay, so what is the meaning of this phi, ma? Tell me. What is the meaning of this phi? Make it fast, ma. What is this phi actually? Maximum number of materials. What Shweta? Number of materials means what? Vedanathan, your answer is correct. Shruti, your answer is correct. Maximum capacity. At the maximum 5 number of materials only can be sent through that particular edge. That is what is the meaning. We can send a maximum 5. That's it. It is not like 5 number of materials are flowing through that edge. Not like that. It is not representing the flow. It is representing only the maximum capacity. Okay. So you have to always, we will be write, that is if suppose if you are writing like this 2 bar 2. Always the numerator represent the flow and the denominator represent the capacity. What is the maximum capacity? Denominator is representing the capacity and numerator will be representing the flow. Okay, ma? And now based on this, all these informations, no, we are going to solve. Okay. Now we are going to solve the problem. Okay. Here we are going to use Q data structure. We are going to use. Listen carefully, student. Only one iteration only I will be explaining you. You have to continue like this for finding the other paths that are available and other flow or otherwise what is the maximum number of meters that can be sent, that you have to do it by yourself. Okay, we don't have time. For finding the augmenting path means the path through which some extra materials that can be sent from the source to the sink. That path, that path is called as augmenting path. What is augmenting path? The path through which some additional materials can be sent from the source to the sink. That is what is called as augmenting path. Now, first of all, we have to find the augmenting path. Then we have to find what is the number of materials that can be sent through that particular augmenting path. Okay. In that way only we have to find the solution to this problem. For that, we have to do the labeling for all the vertices. Okay. So, for all the vertices, we have to give the label. Actually, two labels we will be giving for all the vertices. The first label, it represents the maximum. What is the first label? It represents the maximum number of, that is the number of materials that can enter into the vertex from the source, or otherwise number of materials from source. First label, it represents the number of materials from the source. This is what is the first label. Second label, it represents, okay, vertex from which the material is sent, or the vertex from which the material is received. Vertex from which the material is received. That is what is the second label. For the what is this one? The source vertex. This is what is the source vertex. Okay. So we have to label the source vertex with the label infinity comma null value. Okay. So maximum you can send any number of material to the source vertex, because from here onwards only we are starting the flow. So any number of materials can be given to source vertex. So infinity. And what is the second label? Vertex from which this particular vertex is receiving the material. Okay, it is not receiving material from any other vertex of this particular graph. So the second label is empty. Okay, so infinity comma null value is the label for the first vertex. As I told already, we are going to use the Q data structure. After labeling any vertex, no, that vertex must be inserted into the queue. Now we are inserting vertex number 1 into the queue because we have given label to the first vertex. Now afterwards, what we have to do now? We have to label the. Then in the next step, we have to remove the front element from the queue. What is the front element? Only one element is there. That is vertex number 1 is the front element. So we are removing front element from the queue. Okay, ma? So we are removing front element from the queue. Then afterwards, we have to label the adjacent vertices of the unlabeled adjacent vertices of the front element must be labeled. Okay. What are the adjacent vertices of one? The vertices that are directly connected with 1. 2 is there and 4 is there. These two are the adjacent vertices of 1. Okay. Now we have to label 2 and 4. Here 2 is available in the forward direction from 1. Similarly, 4 is also available in the forward direction from 1. Okay. We have to check for 2 conditions. If those 2 conditions are satisfied only, you can label 2 and 4. And one more thing, you have to remember that whenever you label the vertex, no, that must be inserted into the queue. Okay. So now, what is the first condition for conditions to be checked now? The remaining capacity, whatever the remaining capacity which is available for this particular edge, no, that must be, the remaining capacity must be greater than or equal to 0. The remaining capacity must be greater than or equal to 0. This is one condition. And another condition is the vertex number 2 must be unlabeled vertex. Okay, this is what is the another condition. Okay, so initially we have labeled infinity comma null value for the first vertex, and we have inserted 1 into the queue, and we have removed the front element from the queue, and we are going to label the adjacent vertices of 1. 2 and 4 are going to be labeled. Just like that, we cannot label this 2 and 4 must be unlabeled vertices, and the remaining capacity of the corresponding edges must be greater than 0. In that case only we can label. Okay. Now at present, no, in this, according to this particular graph, no, 0 bar 2 in the sense 0 number of materials we are sending. The flow is 0 number of materials. At present, we are sending only 0 number of materials through this particular edge. The numerator is containing 0. In the sense, what, we are not sending any material. 0 number of materials only we are sending. That is what is the mean. So what is the remaining capacity? The maximum capacity minus the current flow. That will give you the remaining capacity. What is the remaining capacity which is available for this particular edge? 2 minus 0 is equal to 2. Since the remaining capacity 2 is greater than 0, as well as this 2 is an unlabeled vertex, now we can label the second vertex. Okay. Now 2 labels we have to give for the second vertex. What is the second label? From which vertex it is getting material? From vertex number 1 only it is getting material. So 1 you can write. Okay, the second part of the label is 1. In which direction it is receiving material? In positive, that is in forward direction only it is receiving material. So 1 plus, you can write that one as 1 plus. And now the first part, no, how to write this first part now? You have to compare the remaining capacity and the L value of this, the first label of this particular vertex 1. Okay, here it is infinity. What is the remaining capacity? Remaining capacity is 2, which is minimum. Infinity and 2 compare. Which is minimum? 2 is minimum. So you have to write 2 here. Okay, so what is the label of the second vertex? 2 comma 1 plus is the label of second vertex. See here, that is what is the label we are giving here. 2 comma 1 plus is the label of the second vertex. After labeling the second vertex, we have to insert it to the queue. Now we are going to label the fourth vertex. Now tell me, Pa, what is the label we can give for the fourth vertex? What is the second half of the label? From which vertex it is receiving material? From vertex number 1. In which direction? In forward direction only. So 1 plus. What is this value? The first part of the label is what? What is the L value of this particular vertex number 1? Infinity. What is the remaining capacity here? 3 minus 0 is 3. Which is minimum? Infinity and 3 compare? 3 is minimum. So the label is 3 comma 1 plus. This is what is the label for vertex number 4. As I told already, very good, Shruti, 3 comma 1 plus, very good. That is what is the label. And now after that one, no, after labeling that, the vertex number 4 must be inserted into the queue. Okay. Now after deleting the front element from the queue, 1 from the queue, we have labeled the adjacent vertices of 1, 2 and 4 got labeled. Whenever you label the vertex, no, that must be inserted into the queue. So we have inserted into the queue. Now, which is going with, we have to repeat the same steps until the sync vertex got the label. Understand, ma? Okay, till that particular time, we have to repeat the same procedure. Once the sync vertex got the label, which is the sync vertex? Vertex number 6 is the sync vertex. Once the sync vertex got the label, we can stop the operation there itself. Okay. Now, if that is the case, we found an augmenting path. That is what is the meaning. Now, what is the front element now? 2 is the front element. Remove 2 from here. Okay. After removing 2 from here, what are the vertices we have to label? We have, what are the adjacent vertices of 2? 3 and 5 are the adjacent vertices. Even 1 is also adjacent only, but it is labeled already. Infinity comma null value. We have labeled that already. So you cannot label it now. So now we have to label 3 and 5. Tell me what is the label we can give for 3 ma. Make it fast. Use the same procedure and tell me what is the label we can give for 3. Make it fast. From which vertex it is receiving material? From second vertex in forward direction. So 2 plus. Okay. 3 comma 2 plus. Shruti, why you are telling the answer as 5 comma 2 plus? That is not 2 comma 5 comma 2 plus. 2 plus. What is this value? What is the remaining capacity here? 5 minus 0 is 5. What is the L value of the previous vertex 2? It is 2. So you have to compare this 2 and the remaining capacity 5. Which is minimum? 2 is minimum. So I have to write 2 here. So the label of 3 is what? 2 comma 2 plus. Who has given the correct answer? 2 comma 2 plus? Sai Deepika. Very good. So 2 comma 2 plus is the label for 3. So after labeling that one, 3 must be inserted into the queue. Now tell me what is the next vertex to be labeled. 5 is the next vertex to be labeled. Now tell me what is the label for 5. Ma? Tell me the label for 5. It is also getting materials from 2 only in the forward direction. What is the first part of the label? Make it fast. 2 comma 2 plus. Very good. 2 comma 2 plus is the answer. How it is 2 comma 2 plus? L value of the previous vertex is 2. What is the remaining capacity? 3 minus 0 is 3. Minimum is what? 3 and 2 compare. 2 is minimum. So 2 comma 2 plus is the label. Okay. And now 5 is also. After labeling 5, no, that must be inserted into the queue. Now what is the next element to be removed? Front element is what? 4 is the front element. So I am removing 4 from here. Just check the adjacent vertices of 4. How many adjacent vertices are there for 4? Vertex number 1 and vertex number 3. These two are the adjacent vertices. But these two adjacent vertices got the label already. So you cannot label the same vertex once again. It is not possible. So after removing 4, you cannot label the adjacent vertices of 4 because they have got labeled already. Leave it. Now remove the next front element. Next front element is 3. 3 we are removing from here. After removing 3 from here, What are the adjacent vertices that can be labeled? How many adjacent vertices are there for 3? 3 is directly connected with the 4, 2 and 6 also. What about 2 and 4? 2 and 4 got the label already in the previous step itself. So what is the vertex to be labeled now? 6 is the vertex to be labeled. What is the label we can give for 6? Tell me, Pa. From where 6 is going to get the material? After removing 3 only, you are going to label 6. So what is the previous vertex? Yes, it is 3 only. So what is the label? Second half of the label is 3 plus. That is okay. What is the first half of the label for the last vertex 6? 2 comma 3 plus. Very good. Okay. What is the L value of 3? It is 5. Sorry, it is 2. It is 2 comma 2 plus only. It is 2. 2 and remaining capacity, that is also 2. Minimum is also 2. So the label is what? 2 comma 3 plus. This is what is the label for 6. Okay, 6 also can be inserted into the queue. And now, should we repeat the same procedure again, or should we stop the operation here itself? Stop. Why? What is the condition I told already? Once we have reached the sink. That means what? We have labeled the sink. Once we have labeled the sink means, what is the meaning? We found an augmenting path. That is what is the meaning. Augmenting path in the sense what? The path through which some additional materials that can be sent. That is what is the meaning. That is what is called as augmenting path. We found the augmenting path. Now I'm going to erase all path. Okay. Now, whatever the labels we have, we did know, everything is given in this diagram. Okay. Label of this vertex, label of this vertex, label of this one, label of this one, and this one. Now, I'm going to explain how the flow can be identified. What is the L value of the last vertex, 6th, the sink vertex? What is the L value? 2 comma 3 plus. This is what is the label. What is the L value? The first label is called as L value. So what does it mean? Maximum 2 number of materials are reaching the last vertex, sink vertex. That is what is the meaning. The number of materials that are sent to the sink vertex is how much? 2 number of materials are sent. From which vertex the 2 number of materials are sent to 6? 6 is receiving materials from which vertex? It is 3. How you can say that it is reaching? See the second label, 3 plus. From vertex 3 in the forward direction only, vertex number 6 is receiving the material. So just highlight this edge. Understand, ma? I am highlighting that edge. Now see the label of vertex number 3. It is also getting 2 number of materials. From which vertex? See the second part of the label of 3. It is 2 plus. Am I right? Yes or no, ma? See the label of 3. What is the label of 3? It is 2 comma 2 plus. Label of 3 is 2 comma 2 plus. So it is receiving material from the second vertex. So we have to highlight this particular edge. Edge from 2 to 3 we have to highlight. Now check the label of the vertex number 2. It is second half of the label is having 1 plus. In that case, it is receiving material from the first vertex. Highlight this particular path also. Okay. So this is what is the augmenting path. Okay. So from vertex number 1 to 2, 2 number of materials are sent. From 2 to 3, 2 number of materials are sent. And from 3 to 6 also 2 number of materials are sent. So we found the augmenting path, and we found what is the number of materials that are sent through this particular path. That also we found. Okay. And now this flow, we found the flow now. That must be updated in the diagram as the numerator. Only through this particular path, the numerator must be given as 2 bar 2. This must be 2 bar 2. This must be 2 bar 5. This must be updated as 2 bar 2. Understand, pa? That is shown here. That is what is shown here. The flow, what we found already is shown here. See the flow here. 2 bar 2, 2 bar 5, 2 bar 2. So two number of materials are sent through this particular path, augmenting path. So one flow we found 1 to 2, 2 to 3, 2 to 6. How many number of materials we are sending? Two number of materials are sent through this particular path. And this is not the end for this particular problem. We have to repeat the same procedure and we have to identify the other paths that are available, and any other path is available through that particular second path also, how many materials we can send. Okay, that we have to find using the same procedure. Okay, so that is initially we will be giving infinity comma null value for the first vertex. In the queue, 1 will be inserted. Then 1 will be deleted from here. Then you will be labeling 2 and 4. Now tell me whether vertex number 2 can be labeled or not. Tell me, Pa. I told two conditions to be satisfied for forward direction edges. Okay, for labeling the vertices. What is that? The remaining capacity must be greater than 0 and the vertex must be an unlabeled vertex. Adjacent vertex must be an unlabeled vertex and the remaining capacity must be greater than 0. Now my question is, after labeling 1 and after removing the front element 1 from the queue, whether it is possible to label vertex number 2 or not, tell me. Make it fast. I'm not going to explain the full path here. I want to clarify your doubt here. I want to check it out, whether you have listened or not, whether you understood or not. Now tell me whether vertex number 2 can be labeled or not. No one is answering. It is not labeled already. That is previous iteration. Now for the next time, no, we have to start the labeling from here onwards. It is not labeled already, pa. It is unlabeled only. Now only for this second iteration, we are labeling now only. Okay, now only we are going to label. So that is not the reason. See here, no label for 2. We have labeled only the first vertex. What is the remaining capacity? What is the flow which is flowing through? Number of materials that are flowing through here is what? 2. What is the maximum capacity? That is also 2. How to find the remaining capacity? Maximum capacity minus current flow. Denominator minus numerator. What you'll be getting? 2 minus 2, 0 you'll be getting. The remaining capacity is 0 here. So if the remaining capacity must be greater than 0 only, you can label this 2. So now the remaining capacity is 0. So you cannot label 2. You have to label 4 only. What is the label you can give for 4? 3, 1 plus you'll be getting. 4 will be inserted into the queue. And front element 4 will be deleted from here. Then adjacent vertices of 4 will be labeled and so on. In that way, you will continue and you will be finding this particular path. Okay. Through this particular path, only one material can be sent. Okay. And whenever you get backward edge, no, if any backward edge is there, then you should not consider the remaining capacity. For labeling, no, you need not consider the remaining capacity. You have to consider the flow. The flow must be x value. The numerator must be greater than 0. If that is greater than 0, then you can label the adjacent vertex of 3 in the backward direction. That you have to remember. Afterwards, no, after finding this 1, no, this flow 1, no, numerator, this flow must be updated in this particular path. So 0 bar 1 will be written as 1 bar 4. Then this will be written as 1 bar 3. This will be written as, it is not 3 bar 5. In backward direction only, reverse direction only, backward direction only, the material is flowing through this particular edge. So 2 minus 1, 1 bar 5 you have to write here. So you have to be very careful about the backward edges. For the backward edge, whenever you you need to find the flow, no, you have to subtract the flow from the numerator. And here it is forward edge only. 1 to 4, 4 to 3 only the material is flowing. So it is going to be 0 plus 1. Numerator 0 plus 1. Okay, 1 bar 1. Here it is going to be 1 bar 3. So here through this path, no, 1, 4, 3, 2, 5 and 6. Through this particular path, one material is flowing. So totally 3 number of materials are sent. Okay, so this is what is the maximum flow. Okay, so for this also, ma, I will give one problem. You just go through that. That is, you try to solve that particular problem, so that only you'll understand. So in this way, we have to find all the augmenting path and the maximum flow, whichever is possible for the given flow network. That's it. Any doubt, ma? Do you understand this one, ma? Maximum flow problem? No reply, students. So with this, one half of the fourth unit we have completed. Now, in the, two more problems are there, and those problems are that is, one problem is it will take time for solving one problem, but another problem, the second last problem is very simple. Okay, we can complete it very quick. Now you can post the attendance, students. Check it out and tell me whether the link is working or not. Check it out now whether the link is working or not. Okay. And post the problem in the Google Classroom, students. You have to solve and send it to me. Those that submitted the attendance can be. The remaining things we'll see day after tomorrow.